Ma'am, I think we can start now.
Yeah. Okay.
So, good evening, everyone. This is Oricho, and I will be your host for today's session. Our today's session is on asteroids. Can we save our planet from an impact? And our speaker for today is Dr. Priya Hasan. She is the assistant professor at Maulana Azad National University, Hyderabad, India, and co-chair of Women in Astronomy, WGIOU. So, without further ado, I'd request Priya ma'am to start with today's session.
Yeah. Thanks, Abhijit. Thanks so much. And thanks for having me over. Today, we'll be talking about something very, very important. And just a minute, I'll just share my screen. Is all fine? Can you see my screen? Hello?
Yes, ma'am, the screen is
All
visible.
good, huh? All fine. Okay. Yeah. So thanks so much. Thanks, Arithro. Thanks so much, Hex-Star Universe, as well as Citizen Science Group, for inviting me to give this talk today. So today I'll be talking about asteroids, and that's basically because you all know that tomorrow is Asteroid Day. I'll tell you why, and we'll just think. So some of you who are Asterix fans, you would know that in Asterix there's constantly a thing about the sky is about to fall on our heads, right? But in principle, what I want to tell you all in reality, such a threat does occur. It is true that there is a chance of a piece of sky falling on ourselves, and I'll come on to that and why do we actually believe in that. And so therefore, the important question is that if this is what can happen, can we actually save our planet from an impact? That's what we are also going to talk about today. So this talk has been planned specifically because tomorrow, June 30th, is celebrated as Asteroid Day by the UN. This is basically in this is to build up public awareness about the risk of asteroid impacts. This is because the Tunguska event in Siberia. This is in Russia and Siberia in 1908. There was this huge asteroid which fell, and even to date, you can see that the clearing which was caused by it, it still exists, right? Though this is more than 100 years old. And therefore, it is realized that it's very important for us to be aware of asteroids and how very important is it for us to be aware of impacts and some kind of possible mitigation or protection of our planet from such events. Now, all of you all are obviously aware of the dinosaurs who actually went extinct about 65 million years ago. They lived in the planet for about 165 million years. And then we know that there was an asteroid which had a size of about 10 to 15 kilometers, which fell onto the surface. And that's what actually caused the extinction of the dinosaurs. Now, how do we do know this? This is because in rocks which we have, right, in geological records, there is a KPG event which is actually marked by a layer of sediment, okay, which is found in rocks of that age, which is basically indicative of a metal called iridium, which is present in asteroids, which obviously came into these rocks from there. So that is one indicator that this thing did take place. And then the next thing was to look for the impact. Where did the impact take place? And it was found that about 180 kilometers in the Gulf of Mexico, there is this Chicxulub crater, which was found in the 1990s. And this is most probably the point at which this asteroid actually impacted the Earth. So what you have is you just have a 10 to 15-kilometer asteroid falling onto the Earth. Now, the Earth is obviously much larger in size. So you would say, how can such a rock like finish off all the dinosaurs? But the problem is that when such an impact takes place, there's a very large amount of dust which comes into the atmosphere, which you can see in this upper picture. So if you have so much of dust which comes up into the atmosphere, basically it's going to block all the sunlight. Okay. And for the food chain, you need the plants which actually are going to use sunlight to create their, to survive. And then you'll have some dinosaurs which are going to be eating the plants. And then another set of dinosaurs, the carnivorous ones, which are going to eat those, which eat that. So, in short, trees are a very important part of the food chain. And therefore, if you block sunlight, that is, you make it unable for the tree to produce its own food, you break the food chain. And that's how the dinosaurs went extinct, right? It's not that this 15-kilometer dinosaur fell on sorry, crater fell on a dinosaur's head. It's just that it created this whole dust envelope around the earth, which stopped sunlight from coming onto the earth, which then broke the food chain and which caused the extinction of the dinosaurs. Now, we know in India also there is the Lonar Lake, which is in Maharashtra. And you can actually see this is a satellite image. You can perfectly see near circular this thing. This is the lake. Again, you can see it's quite circular. This is in the Lonar in Budala district in Maharashtra. And it was suspected as to this is also the point of some kind of an impact. And then when there were further studies made about it, it's quite a large thing. It has a diameter of about 1.2 kilometers. And what they actually found is that the kind of minerals present in the water, etc., over here, these are typically the kinds which would get from asteroids, which explains that the lunar crater probably formed because of an asteroid impact. So we already have examples of asteroid impacts in, which have happened in the, kind of recent past. And if you actually see in terms of size and frequency, every day the Earth is bombarded with more than 100 tons of gas and sand sized particles. About once a year, you have a car sized asteroid which actually falls. But the problem is with such a asteroid, if it's the size of a car, what would happen is it would basically be there'd be so much of friction in the atmosphere when it enters that you'll just have a large fireball, which is what we call our shooting stars. Shooting stars are formed by smaller asteroids, so they just burn up in the sky, and you see this, the shooting star which shows up, which is basically the asteroid burning in when it enters inside, right? So most of them are small and they are harmless, even if it's a star size. But about every 2,000 years or so, you could have a meteorite which is the size of, say, a football field, which is much larger, and that can actually cause damage to an area locally to that area, something like the Tunguska event. And then about once in every million years, you could have something which is large enough, which can actually threaten civilization. For example, the ones that the one that caused the extinction of the dinosaurs. Now, space rocks, if they're smaller than about 25 meters, they'll actually burn up in the Earth's atmosphere. And there's almost no damage. Similarly, if you had a meteorite between 25 meters to about 1 kilometer, also, right? In that case, it will just cause a local damage, right? Like the Tunguska event. But for example, if you'd had anything larger than 1 or 2 kilometers, this would cause a worldwide effect. So if you could, and such a thing like we saw in other things, it could happen, say, once in a few million years. You could have this kind of a thing happening. But once every 2,000 years, you could have the size of a football field, which could come in, right? And so therefore, any asteroid of that kind of size could have worldwide effects. And by comparison, asteroids that populate the main, actually the asteroids which we know, which are between the orbit of Mars and Jupiter, these are much larger in size. But because they are far from us, they could be as large as 940 kilometers. But because they are large, they are not much of a threat. We basically need to worry about the ones that come, into the Earth's orbit, right? Which come. So let's come to the main question: what are asteroids, and where do these asteroids, where do these strange, pieces of rock, where do they come from? So about a long time back ago, when you look at the origin of the solar system, right, we know that the solar system formed from what is called the solar nebula, which is basically made up of gas and dust. And you had this rotating disk, right, which is what is called a protoplanetary disk, the center of which you have the star forming. So this is the sun forming in the center, and you have a lot of these rocks and this debris which is going around it, which is the protoplanetary disk. Now, when the sun gets formed, this is the sun is already born, you have these protoplanetary disks forming into planets. So what happens? They accrete and form into a solid structure. And when the solid structure forms, it kind of clears off the material between them, right? So you can see that the material between them is getting cleared, and you can have the planets forming in orbits, right, which are here. So you have the sun, you have Mercury, Venus, Earth, you have all the planets forming, right? But while they formed, you can see that the large amount of this material is still rocks, right? And therefore, they are still found in our solar system. So, for example, we have an asteroid belt which lies between the orbits of Mars and Jupiter, right? And then you have another belt which is beyond the orbit of Neptune, which is called the Kuiper belt. Again, we have asteroids over here. And then you have one which is at much larger distance, which is at about 1,000 times the distance between the Earth and the Sun. So here you can see something called AU. AU is an astronomical unit, which is the distance between the Earth and the Sun, which is 150 million kilometers. So the Oort's cloud is at a distance of about 100,000 AU, which is much further away, but it's a large structure for which you can have these. So you have objects in the Oort's cloud, you have some in the Kuiper belt, and you have some of them between Mars and Jupiter, and then you have a few of them scattered around. So if you were actually look at the solar system, you have the Sun, Mercury, Venus, Earth. You, like I told you, between Mars and Jupiter, you have these ones, the asteroids, and then Jupiter's orbit, you have the Trojan satellites, which are over here, which are at what are called the Lagrange points at 60 degrees, right? And then you have a lot of this leftover debris, which is there from the time of the formation of the solar system, which is lying around over here. And this is this debris which can come into the Earth's orbit and what we are actually concerned about. So, for example, Mars itself has two satellites, Phobos and Deimos, and these are basically captured asteroids, which they got from the which Mars probably captured from the asteroid belt. So, if you look at the picture of this is an older animation, which actually shows you a picture of the amount of asteroids which we know. So, you can actually see that asteroids have been very carefully tabulated in such a way that the blue is the near Earth asteroids, while orange is the main belt asteroids between Mars and Jupiter. So you can see over here, here is the Sun, you have Mercury, Venus, you have the Earth, and you can see that there are a large number of known asteroids. These are tabulated, catalogued asteroids, right? So we know that these very well exist. We kind of know their orbits also. So we know in which way they move. And you can see that these are the large number of this thing. So these are the ones which are closer to the Earth, the blue ones, and the orange ones are the ones between Mars and Jupiter's orbits, right? So you can see that you have a good number of these. And as the Earth is going around the Sun, there are points in which it's going to go through more of these, right? So we know that asteroids are therefore leftovers from the formation of our solar system, which is about 4.6 billion years old. And the birth of Jupiter, because you had Jupiter as such a massive planet, you probably the asteroid belt between Mars and Jupiter is either it is a planet which never formed, basically because Jupiter's gravitational force was very strong, and therefore you have the Sun and you have Jupiter both kind of pulling in opposite directions, due to which you have the asteroid belt forming. And therefore, while we are trying to study how our solar system formed, it's also important to obviously study these asteroids because these are leftovers from the time of formation. So we want to see how our solar system was at the time it was formed. We can actually see it by seeing the position of these asteroids and how are they, what are they like. And what are these asteroids like? So basically, asteroids are irregularly shaped. Some of them are spherical, like one of the largest ones, which is called Ceres. This is quite spherical. But many of them actually have pits or craters on them. That's because these guys, they're basically moving freely in space and they can have impacts from various objects, right? So as the asteroids revolve around the sun in their elliptical orbits, some of them also rotate and some of them can actually tumble and they can collide with one another. Some of them may be even binary or double asteroids or multiple systems. You could also have triple asteroids. And typically, the surface temperature of an asteroid, it's very cold. It's about minus 73 degrees Celsius. It's a cold object. And asteroids have stayed mostly unchanged for years. And therefore, it's interesting to study asteroids because they can actually tell us some good information about our solar system itself. And like I mentioned, they come in a variety of shapes and sizes, and some of them also have moons. There are various types of asteroids. We actually categorize them. For example, they're the C type, which are the carbonaceous asteroids, which are grayish in color. They are basically 75% of the known asteroids are all C type asteroids. They are made up of clay, stony silicate rocks. There are also what are called the S type or silicious asteroids, which are greenish to reddish in color. 17% of the known asteroids are that. And there's a small chunk of asteroids, which are the M type or metallic one, made up of metals, and they are often iron or nickel rich. And then there could be some made up of still more, rare types. For example, made up of basaltic volcanic crust and various other materials. And these minor planets, they're called minor planets. They also include asteroids. We have a lot of minor planets which are found. They are basically asteroids. And you have these near Earth. They are categorized as near Earth objects, mass crossers, main belt asteroids, Jupiter Trojans, etc. And there are millions of asteroids ranging in size from hundreds to several miles across. But in total, the mass of all the asteroids is less than that of the Earth's moon, right? So the total mass is not much. Now, why is it important to study asteroids? So, first of all, is that they have very potent, important information about the nebular phase of the solar system and the solar system was forming. It basically carries that vital information. Another very important thing is that they are also thought they could be possible bearers of carbon-based materials or material which would be getting life on Earth. And then you need to monitor them because these are the kinds of objects which can actually cause mass extinction on the Earth. And then there's a newer interest which people have even about of mining asteroids. That if asteroids are made up of rare metals, then there could be even a probability of mining them to get these rare metals, right? And now we classify asteroids into various types. For example, Amor asteroids. These are ones which have orbits between the Earth, but they basically lie between Earth and Mars. Okay, so they don't come close. Apollo asteroids, they cross the Earth's cross orbits, but most of the time they spend outside the spot. 18 asteroids, they cross Earth's orbit, but spend most of the time inside Earth's orbit. And then Atira asteroids are the near Earth asteroids whose orbits are contained within the Earth's orbits. And therefore, these Atira asteroids are the ones which we need to be most concerned about, the Atira and Aten asteroids, because these are the ones which are closer to our orbit. And of October 2021, we already have more than 27,000 known asteroids which have been categorized and actually put into these things. Now, how do you actually look for asteroids? So it's said that more than 200 years back, you had an Italian astronomer, PRC, who actually discovered the first known asteroid series because it is between the orbit of Mars and Jupiter. But this is a reasonably large asteroid, and instead it's nowadays classified more as a dwarf planet, okay, because it's so large. And since about that, you have NASA doing various programs. We'll talk about them. For example, the Catalina Sky Survey, the Pan-STARRS, and there are various surveys which are actually being done to look for asteroids. Right? I'll show you in what way. But typically, when you're looking for asteroids, Ceres has a diameter greater than 900 kilometers. So you see that the number of asteroids is only one Ceres type. But as you reduce the diameter of the asteroids, you can see that the number of them, this is MLN as million. So you can see I have about 100 million when you're going to about a size of about zero point 0.1 kilometers. And as you're increasing the size, the number of asteroids reduces, right? So the typical known asteroids, the largest ones we know, Ceres is the largest one, and this basically has a diameter is about 27% of the moon, right? And but then you also have these other large uh, asteroids, for example, Vesta, Pallas, Hygiea. These are also a decent, reasonable fraction of the size of the moon, which masses ranging in this densities, something like this, right? And and we come up to the most important question: is can these asteroids hit the Earth? Now, I showed you first, for example, the first important example was the one of the dinosaurs, and then the example which I showed you of Lunar Lake, which clearly shows you that we have already had such asteroid impacts. So the answer to this question is obviously that yes, the Earth formed 4.5 billion years ago, and we routinely have asteroids and comets which have fallen onto the Earth, right? And obviously, dangerous ones are rare, but it can happen. So typically, if you're looking for asteroids which are capable of global disasters, they are typically the ones which are about half a kilometer size, 1 kilometer size. These are the ones which can actually create a very big impact, right? It can create what is called that nuclear winter, which I told you is you basically the impact will raise so much of dust that it will cover up the planet and not allow sunlight to fall inside it, right? So asteroids are classified as near Earth asteroids. These are class obviously asteroids which are closer to the Earth. But of the nearer asteroids, what we need to be really worried about are what are called the potentially hazardous asteroids, or the PHAs. These are ones which come into orbits which are 0.05 AU, right? Which is about 7.5 million kilometers. So if an asteroid comes within 7.5 million kilometers, that's the case in which we call it a potentially hazardous asteroid, for which we actually need to worry about how would we actually, protect the Earth, or what is the probability of a collision. Now, some of you all may have actually seen this, an interesting movie. I would urge people to see it. It's called Don't Look Up. It's a movie on Netflix, which is basically the story of a possible story where a PhD student, she actually, while observing with the Subaru telescope, she observes an object which is identified to be an asteroid. Now, with her supervisor, together they calculate the orbit of this asteroid, and they realize that this asteroid is on a head on collision. It's going to come and hit the Earth within 6 months. And the story, basically, Don't Look Up, is basically showing us how badly we are prepared for such a possible event. Because what is shown in the movie is shown that when these astronomers, they are calling out to people, telling them that, this is what is going to happen, they see that even the president of the country is not concerned about it at all. The president is worried about her position in the elections, and there are people concerned about all kinds of other things, and nobody seems to be wanting to listen to these people. And therefore, yeah, part of this talk and this process is basically to build up people's awareness about the possibility of this event, so that we actually prepare ourselves in some way, in seeing what can we actually do. And preparations are already on. I'll show you what kind of things are being done. But it is very important, what the movie also kind tries to convey, that it's very important that we aware about this, and also important about us trying to actually look for some methods or some ways of actually, seeing how can we, protect the planet from such a possible event, right? That is very important, and that is what is the importance of even having this talk, right? So, like I mentioned earlier, that smaller asteroids, if they hit the Earth, that's not too much of a problem, because they would could probably strike once every 1,000 to 10,000 years. They could destroy a city or something like that. But even recently, in the year 2013, right? In the year 2013, an asteroid actually fell in. Again, this was in Russia, in the Russian city of Chelyabinsk, and it created a shock wave, and it is found that in this, luckily nobody died. It actually injured a few people, because you had, the shock wave actually broke some glass and things like that, but it was enough to get people worried. So this rock was not very large. It's about only 20 meters in size, but you can see that it actually, it just happened 10 years ago. So something like that can happen even often enough. Now, what is a meteorite? Is that when this asteroid falls from the sky, if it crashes onto the Earth, that means it lands on the Earth, right? If it lands on the Earth, then we call it a meteorite, right? Now, what are meteorites? So we know what are meteorites, so you can actually see them. Some of them are made up of iron, right? Some of them are stony ones with oxygen, silicon, magnesium, and some of them are made up of nickel, calcium. So you have a whole lot of meteorites which we do find on the Earth, for which we actually, interesting thing is that not all of this is always very devastating, right? One of the most accepted theories about how the Earth got water is that most probably the Earth was actually dry and barren, right? But it's a possible asteroid or a comet collision which could have actually delivered water, ice, and other carbon molecules to the planet, that number one could have actually caused life, got life to the Earth, and number two, it made the planet habitable. That means you could have life surviving onto this thing. So a possibility is that one of the possible theories of the origin of life on the Earth is that you could have these impacting comets or asteroids which came in, and they actually got life onto the Earth about 3.5 to 3.8 billion years ago. And that's also, again, the reason for why we have uh, water, right? So, not always is this thing very devastating. Like in this case, it is actually life giving. But the question is that now, if now we already have life on the earth, but now obviously we won't be too happy with having this huge asteroid falling on us, and therefore we need to actually look for them. Now, when the asteroids actually do close flybys, one of the most effective ways is to observe them. You can use a radar. So even in 2017, there was this asteroid called 3122 Florence, which was actually observed with a radar. And with the radar, you can actually, it was found to be at a distance of 7 million kilometers, which is, safe enough for us. But you could actually get the size of the asteroid, 4.5 kilometers, and its shape, etc. As well as this asteroid had two moons also, right? And therefore, you can actually, a radar can actually give you a good idea of asteroids. NASA actually has a website which is for Planetary Defense Coordination Office, which is basically the IDA collaboration, Asteroid Impact and Deflection Assessment collaboration. And you also have various activities happening by ESA, the European Space Agency, the German Aerospace Center, the French one at Côte d'Azur, the John Hopkins University. So the important thing is that we actually need to detect them well in advance so that you can have the first step is to detect and then to do a rapid response, right? So that you can actually protect the planet, right? So if you actually see this is a website, you can have a look at it up the top, which is called the Planetary Defense Coordination Office. And you can see that over here, people can actually, there are observations of near Earth observations, various images, etc., of materials which people have seen and put over there. They all categorized and put over this. So your potentially hazardous objects, everything is entered into this so that the data is present, right? Now, what would we do if we have to protect ourselves? Say we know now, let's say we detect an asteroid which is coming, and what do we now do to protect the planet, right? So people came up with all kinds of ideas as to what can be done. So one of the ideas, for example, is called slice and dice. What is slice and dice? Is that you send off small rockets onto the asteroid surface, right? So you see over here, you have these little rockets which fall on the asteroid. You have this rocket which throws these little arrows which shoot into the asteroid, and this thing would actually deploy dozens of spear like penetrator rods. So basically it breaks the rock into 100 pieces, and in that way you can actually slice and dice the asteroid, right? You just break it into bits. The other way, which is to paint. Supposing you spray paint an asteroid, you send spray paint over there. Then what happens is with paint, there's an interesting thing. There's something called albedo. Albedo is the reflection, the absorption. How much of reflection, how much of absorption takes place. So, for example, if you have a dark space, a surface, it reflects less. It absorbs more light. If you have a lighter surface, it will reflect more. So, what happens is there's something which we'll talk about in a bit, which is called the Yarkovsky effect, that which happens with asteroids because they, depending on whether they are facing the sun or not, some part of the asteroid gets hotter, some part of the asteroid gets colder, and that is why what happens is the path of asteroids kind of alters regularly. It's not a very regular orbit. It keeps changing because of the unequal heating of the asteroid. So one option is you paint the asteroid so that part of it is hot, part of it is cold, and then you can alter the path. Basically, what you want to do is you just need to change the path of the asteroid so that it does not come and hit the Earth. That's all you need. Another thing which is there in science fiction movies like Star Trek and Star Wars is a gravity tractor. So you have a tractor kind of a thing which pulls with gravitational force. It actually pulls the thing, right? So you have a robotic probe which would beat up with a space rock, and then it will actually pull it. And basically, with that, it can pull the asteroid from its path and change its path, right? Another interesting method people have suggested is what is called ion propulsion. That means you could actually use charged or electrified molecules, and they can actually cause a propulsion which will basically kind of detour to this thing. So there was a NASA Dawn spacecraft which actually did it. Okay, it did it for its mission. It tried it out on these two space rocks, which is Ceres and Vesta, and it actually used it to try and deflect its this thing, which worked out quite well. Another interesting method is called laser ablation method, where, for example, you have CubeSats, right? Let's say you have CubeSats which go and surround the asteroid, and they laser one part of the asteroid. So all these CubeSats together, they point a laser beam on some part of the asteroid, and that will actually cause ablation, or it will kind of break the asteroid. It will cause a dent or something like this, which will actually change the path of the asteroid, right? So that is the laser ablation method. Another interesting thing. See, this may sound science fictiony, but these things are actually in trial. People are trying out these kind of things, and possibly they could be in the future, because a lot of things which were thought of as science fiction, like even man walking on the moon, actually turned into reality. So, some of these methods actually may be something that could be deployed. So, for example, an asteroid tether is basically like a net, right? So, you make a kind of a net. You need to plan what material to make it of, how strong should it be, and how would that net actually nudge it. Now, something like this was actually something very useful and required, that many of you all know that there's a lot of space debris. There's a lot of debris lying around in space, and what we basically need is we need to clear up this debris, right? Because for all new satellite launches and all that, you could always have collisions with the debris. So this is what is called the wrangler, or the weightless rendezvous and net grapple to limit excess rotation system. So this was actually tried out by NASA, right? So that this could be as a good way of clearing up space junk, right? So you have this huge net with which you can clear up space junk. And then another very effective method, which is thought of protecting us from asteroids, which is called a kinetic impactor, right? And today I'm going to talk about the DART mission, which is a kinetic impactor mission, which basically means that you hit an asteroid, a non-destructive project, you hit it, and with the hit, you see how does it change its orbit. And as long as it changes its orbit and it's not a threat to the Earth, your job is done, right? So to sum up, there are different ways of protecting the Earth from asteroids. While so, like I said, this one is not a very feasible one. You actually have a nearby nuclear explosion. You send a nuclear bomb onto it. You bomb it off. That has happened in a few Hollywood movies, but this is not something people would like doing, because you'll have to put the bomb on the rocket and send it. It's not a very nice thing to do. The gravity tractor is what I showed you, which is there in many science fiction movies. And then there is the kinetic impactor, which is this. And therefore, this sounded very a good potential, very doable. And therefore, NASA actually tried out option number three, which is crash into and deviate. So what NASA did is they launched a spacecraft called DART, which I'll talk to you about, and they actually tried to do this. So we'll see a little bit about DART. I'll tell you. But before we do that, we need to know what are these asteroids made up of, right? We've spoken a little about it, but we need to actually check what they are, because that will tell us how can we deflect them, right? If you know what are they basically made up of. So there have been various missions which have been actually sent to explore asteroids. So, for example, way back in 1991, this is like 30 years ago, you already had NASA sent a mission which was called Galileo, which was discovered the first moon to orbit an asteroid in 1994. Then in 2001, you had NASA's NEAR spacecraft, which actually studied the near Earth asteroid Eros for more than a year. And it did not land on it, but it touched down, setting the record to successfully land on an asteroid. In 2006, Japan sent a mission called Hayabusa, which was the first spacecraft to land and take off from an asteroid when it visited its near Earth asteroid Itokawa. Although the spacecraft encountered a series of technical glitches, it returned a small amount of asteroid material to the Earth in June 2010. And then in 2007, NASA had a mission called Dawn. And the Dawn mission, it went to the asteroid belt. This is the one in which I was telling about the ion propulsion, and began exploring Vesta in 2011 and left the asteroid for a trip to Ceres. It studied in 2015, and the mission ended. It ran out of fuel, but it's still orbiting around somewhere in that vicinity. In 2005, NASA sent a mission called Deep Impact, and basically what that did is it basically hit a 370 kg copper impactor into a comet, Tempel 1. This was basically to study the composition of comets, and caused a crater. But there was so much of gas and dust which came out of it that it could not study the crater. It caused a very small change in orbit, 10 centimeters change in orbit, and a very small change in the velocity. Okay. And therefore, what happened is there was a sequel to Deep Impact, and the sequel was a mission called Stardust, which was in 2011. And this mission went back to Temple 1 to actually study the scar which was caused by the earlier mission, which is the Deep Impact mission. right? Japan also had a follow up to Hayabusa called Hayabusa 2, which is this thing. And you had in 2016, NASA sent another mission called Osiris Rex to explore the asteroid called Bennu. Okay. Now, Hayabusa 2, like I mentioned, it's a Japanese spacecraft. It studied the asteroid Regus, collected samples, got them back, and we have various samples from this mission. Osiris X also reached Bennu and would return this year. It will return the samples which are there from Bennu. So, what was the DART mission? We'll talk about that because that is the most recent one. It is basically a kinetic impact mitigation technique using a spacecraft to actually deflect an asteroid. So, what is it? It's basically the double asteroid redirection test. That is DART. Okay. So, let us see what is DART. Um, so, in November 2021, you had this mission launched, and this basically went to a double asteroid. Okay. So you have an asteroid called Didymos, and it has a satellite called Dimorphos, which this thing's around it. So this was a typical kind of it's about 1 kilometer in diameter, and the moon is about 160 meters in diameter, with a period of 11 hours 55 minutes. So it was a satellite with a asteroid, because when you see the deflection, you need to do it with reference to what, right? So in a binary system, it's very easy to define what is the orbit, where is it. So you can then see when it's deflected, where did it get deflected, and what's actually happening, right? So what was the experiment? You launched it in 2021 November, and then in September 2022, the DART, the thing actually crashed into Dimorphos. Dimorphos is the satellite, okay, with a speed of about 6.1 kilometers per second. And then the problem was to check as to what is the deflection it caused, right? How much of a deflection does it cause in the orbit of Dimorphos, right? Of the Didymos, right? And Dimorphos. So here is the thing. If you actually have a look at it, you can see that here's a good this thing of the mission. So, like I told you, the mission is basically, here's the launch of the mission, like I told you, which took place in November 2021. Here's the dark mission, and it's going towards Dimorphos and Didymos, right? This is a double asteroid system. That means an asteroid with a satellite, right? Now, while it goes into it, it actually slams onto it. I told you in September 2022. So here it hits onto it. Before the impact, you had a CubeSat called Lucia, which is the camera, which basically does the camera job of observing it, right? So you have Lucia, which is, I'll show you in a minute. So you have this impact taking place, and Lycia Cube is the CubeSat, which actually does the observations of the impact. So, like I told you, this is the system. Here you have Didymos, Dimorphos and Didymos. So you have the original impact, and then after a certain point, you actually have an impact. You hit the satellite, and the idea is to check what is the change in orbit. Because here, what we want to do is we want to calculate what is the actual change in kinetic energy which you're going to have because of the impact. Because you want to know that if there is an asteroid and we hit it with a certain speed, then how successful can we be in changing its path, right? Because that's what we need to do. If there's we just, all we need to do is change the path so that you do not have this impact, right? You don't have the impact of this asteroid. So okay, I'll just run this a little ahead over here, and here you can see there's a change in okay, here I can move it a little bit here. Maybe let me do this. So after the impact, you can see there's a change in orbit, which is the new orbit, right? So, like you said, this is in principle not so gentle nudge, which is being happening. So you have Didymos and you have Dimorphos. You do this thing, and Lycia Cube. The job of Lycia Cube was basically to photograph and observe the impact, right? And uh, yeah. I was telling you about the Yarkovsky effect, that typically asteroids, the problem is that because while they're going around the sun, because their orbits are not well defined, part of it gets heated, part of it gets cooled. And therefore, you can, the hot part and the cold part, there'll be a slight tug adding on because of that, which will be an additional term to the gravitational force. And therefore, what happens is that because of that, you could have a different orbit of the of the asteroid in different seasons, depending on its position around the sun, right? That could actually vary. And so Lycia Cube, this was the CubeSat which was doing the photography of the impact. So Lycia Cube, which is about 55 kilometers from Dimorphos, it you can see it's detached. See, this is the point at which Lycia Cube came out from the dart thing, and now it's actually going to take images of the impact, and that's what Lycia Cube did. So we have very good images and very good data about the impact. Where did it take place, with what velocity, etc. All that which was data collected by Lycia Cube, right? Now, Atlas is a asteroid terrestrial impact alert system, which is actually a collaboration between NASA and the University of Hawaii. And you can see that the Atlas telescopes, which are located in Hawaii, they took excellent images of this impact. So you can see this is an image of the impact, and you can see after the impact how much of dust came out from the this thing asteroid because of the impact. So this is an impact, and at that point of time, a large number of ground-based telescopes, etc., were actually trying to observe the impact and see what is the effect of the impact. Right. Similarly, not just Atlas, but you have this is an image from the James Webb Space Telescope. It also observed the impact, and basically, what you can see is that a large amount of material got out from the system because of this, and you have extreme brightening happening over there. Now let's remember that James Webb is basically an infrared telescope, and therefore it's going to very well observe gas and dust, and that's what it does. It basically tells you that there's so much of gas and dust coming out over here. Similarly, it was also observed by the Hubble Space Telescope, which you can see over here. Again, you can see a large amount of dust coming out from the thing. This animation, it spans from 20 minutes after the impact, 22 minutes, to about 8.2 hours after collision takes place, where you can see this large amount of gas and dust coming out. This is from the HST, Hubble Space Telescope. Why do we observe with both of this? Because the Hubble Space is going to basically observe in optical, while James Webb is observing in infrared, so we can see the gas and dust. And what is being done with those images? Basically, like I said, what we need to do is we need to make a calculation of the impact. How much of kinetic energy is being transferred by the impact onto the thing because of the collision, right? How can you estimate that? That if you're looking at the material which is ejected, I showed you in that, you basically need to make very meticulous calculations of how fast was it ejected, what was the material which got ejected, how much of what was the speed and how much of it came out. And by observing it in different wavelengths, in infrared and invisible, you are seeing it in different components of that gas and dust, which will actually give you data also about the size of the particles in the expanding dust cloud and tell you about how is this thing coming out, right? So that's why you need to observe it with different telescopes and different wavelengths to actually check how can the kinetic impact modify an asteroid's object. That is the basic question we are asking. Okay, can a kinetic impact modify the asteroid's object? And if it can modify the asteroid's orbit, can it do it by a sufficient amount that we require? Right? That's what we do. So there is a sum up of the result of DART, where you can see is that, like I told you, the orbital period was about 11 hours 55 minutes, and there's a change in it almost by 32 minutes, which was caused by the impact. What was expected originally was that the change would be barely 1 minute and 30 seconds, but what is actually found by observations of these is that the change is about 32 minutes. That means it has an excellent result. It actually did a very good job. Now, other than the DART mission, there are various other missions also which are trying to observe it. So the Lucy mission also, which is a mission which is trying to study asteroids in the asteroid belt, and this was actually launched way back in October 2021, and it's actually going to. These are the Trojan satellites, which are the Lagrange points from Jupiter. So you actually have asteroids over here and here. They are called the Trojan asteroids. So what Lucy is doing is it's actually doing flybys to both these asteroids, and it's actually going to observe them and actually get various data about these asteroids. Right, Lucy. There's another planned mission which is planned in this year. This was the tentative launch date. I don't know whether it's going to happen this year, but it's tentatively this thing to explore the origin of planetary cores by studying a metallic asteroid. called Psyche. And then comes the important question about, can we mine asteroids? Like I told you, a lot of these asteroids have very rare metals in it. And actually, in that Netflix movie, Don't Look Up, which I showed you, the idea of the best friend of the president, who's a billionaire, was that let the impact take place so that they can mine that asteroid and make billions more, right? So actually, people are thinking of how can you extract resources from asteroids, water itself, as well as various metals. And there's actually a whole bunch of asteroid mining can actually create $1 trillion industry. There are actually price tags on asteroids, but depending on their materials, and there are various startups which are actually starting off on how can you actually look for present day asteroids and do something with them. You know, for look for platinum rich asteroids, etc., and mine them. Now we come to an important part where you can play a role. How do you actually detect asteroids? Now asteroids are mainly detected by their shift. So I'll show you an image. Supposing you take successive images of the same part of the sky, you will see that the stars will not move much, but because the asteroid is close to you, it's going to move very fast, right? So I'll show you. So what people do, there are various projects where people take constant images of the sky, of the same part of the sky, and you look for fast moving objects in that part of the sky, and that can actually give you the position of asteroids. So there is the NEOWISE project, which is basically using data from the WISE mission, which is an infrared data mission launched in December 2009. It observes the skies in infrared bands and actually looks for such objects, because such objects will very nicely show up in infrared wavelengths, right? So WISE is very good. You have this MIT Hawaii survey also, which is a spectroscopic survey, again for looking for near Earth objects, NEOs. Then there are various tracking survey projects. For example, I mentioned earlier also, which is part of the Planetary Defense Asteroid Hunters Minor Planet Center. There's the Catalina Sky Survey. There's the Pan-STAR Sky Survey, the Atlas Survey, the Linear Survey. Essentially, what they do is that they take lots of images of the sky, the same region, and they look for moving objects, fast-moving objects, which can be potential asteroids. And then they do follow up missions. Once you observe something like that, you have various telescopes which are actually, for example, the Space Watch Astronomical Research Institute, or the Las Cumbres Observatory, or the Magdalena Rich Observatory, the Manos Observatory. They do follow up missions for the ones which have been observed. You also have radars being used, like the JPL radar, Goldstone radar, etc., which actually try to observe these. Canada has a NEOSTAT program, and there's already launched a NASA this thing called the Neo Surveyor, whose job is to actually look for objects. And then there's something very interesting for which part of the organizers, Dr. Sovam Acharya, the Citizen Science Project, they have a very active group which actually works on the asteroid hunting project, which is called Astrometrica. So here's an example of an asteroid. You can see that over here, these all the stars are stationary. But if you can observe in the center of this frame, you can see this object which is moving. And this is the asteroid. Now, the problem is the number of images we have. We have the Catalina Sky Survey, the Zwicky Sky Survey, the Pan-STAR Sky Survey. There are various sky surveys which are going on. But obviously, the amount of astronomers is not enough to actually look for these moving objects of this kind, right, in the surveys. And therefore, for example, there is an asteroid hunting project, which is a citizen science project. If you want to participate in it, you can contact the organizers. You can be part of this. And what happens is you are actually trained by them as to how to actually look for asteroids. What you need for this is you need to have a desktop or a laptop of your own with Windows so that you can install this Astrometrica software. And with this, you can blink your images so that you can look for asteroids. And this has been a very effective way of actually looking for asteroids. And a whole number of asteroids have been found using this. And I also tried it out with the group to actually look for it. But I was just told that, for example, Astrometrica, you need to have a laptop or a desktop. But Zoo Universe has some more asteroid hunting projects which can be accessed with a mobile phone. So one is called the Active Asteroid, and the other one is called the Daily Minor Planet. So these are very simple. You can just install this onto your smartphone, right? And whenever you have free time, instead of accessing WhatsApp or Facebook, you can actually access this thing. There are many citizen science projects, not just this, which are also accessible through smartphones, so that you can actually use your time effectively to look for this. Now, once you identify an asteroid, there's a very clear, defined method of how do you check on this data, report this data to the main organizers, and then they further explore it and check upon it to see what is it. And in case your object, whichever you identify, is identified to be a real asteroid, a potential asteroid, then you also you are declared the discoverer. You can name the object subject to the approval of the International Space Astronomical Union and the Minor Planet Center. This is again another website which you can have a look on the net. This actually will put up the data of your object, which will have data about the object, its size, its orbit, and what's the distance from the Earth, etc. It will add on to the Minor Planet Center data. So what happens is this is the big database which has information about all such objects and which can be used by people, right? So, and amateur astronomers have been very effective in contributing to projects like this. So, for example, the set of amateur astronomers with just 3-inch telescopes, right? This is a very small telescope. With just 3-inch telescopes, they actually found a main belt asteroid which actually had a small companion, right? So, even if you have a small telescope, like for example, in this case, it's just a 3-inch telescope, with a small telescope also, even if you're not part of those earlier citizen science projects which I was telling you, Astrometrica, etc. You can individually also have your own plan with which you can use a small size telescope to actually look for this asteroid. So once you find a potential object, you report it to the Minor Planet Center. The Minor Planet Center then does follow up observations of the object, with which they actually find out parameters for the object, its orbit, its size, etc., its distance, and you can contribute to something very meaningful and very important to everyone. Now there is the Atlas, which I mentioned earlier. They have dedicated telescopes which are only looking at such things. So they also looked at the DART mission thing, and they're looking at other potential asteroids. So let's get back to DART. Did the DART mission work? How much energy was transferred? Would it be sufficient to protect the Earth in case of an asteroid threat? Now, the answer to this question is yes, the DART mission was very successful. It could show how we could alter the asteroid's orbit by 32 minutes, right? Shortening it had an orbit of 11 hours 55 minutes. It shortened it to 11 hours 23 minutes. This was 25 times greater than what was expected. So it was effective. And now there is a sequel mission called the Hera mission, which is again by the European Space Agency. This is planned for next year. And it's basically again to go back to the same asteroid system because by now, hopefully, the dust should have settled down. And in this case, now it's going to make better measurements of the orbit of Didymos to actually get even better estimates of what was the total impact which we got uh, from the DART mission. So, to sum up, we know that it is necessary for us to observe asteroids, to actually identify them, to check their orbits, see if there's a collision path. If there's a collision path, we need to check out what is the defense mechanism we kind of do. Now, in this case, what happens is the bigger the asteroid, it is easier to detect it, but it's obviously more difficult to deflect it, right? So, the problem is if you see a big asteroid, you detect it, but deflecting it is tougher because the impact has to be this thing. But we still do not know very well what is the limiting mass. Is there a mass beyond which we cannot deflect the asteroid? Or how do we have to plan the timing? When do you plan the impact of the asteroid so that you can deflect it best, with least energy, with least this thing? And I would urge all of you all to actually have a look at this website, which is the CNEOS, this thing, which is run by the Jet Propulsion Lab. CNEOS, this is the near Earth objects. This is basically the catalog of it, where you actually have a catalog of these objects. What are their diameters? How often they hit the Earth? What is the impact energy? What is the population, etc. And one can actually study these objects, catalog them, and be well prepared for something which could be devastating in the future, right? So that's the basic purpose of having this website. And so I'll end with this, that we have exciting times ahead. We know that there is a potential threat to the Earth because you could have these asteroids coming in. But we also know that we have already begun efforts in actually trying to think of how can we actually protect the Earth from such an impact. We need to do obviously more work about it. And like I said, what's exciting about this is that this is something in which even non astronomers, for example, citizen scientists, amateur astronomers, can also play a very, very important role in this. Because the problem is, you have to search through data. You're looking through data of Pan-STARRS, Catalinas, Wiki survey, various things where you're actually looking through data, looking for these objects, and the number of objects is huge. And we therefore participation from citizen science projects as well as amateur astronomers is also very important in this basic in this area of astronomy. So thank you. I'll stop with this and I'd be happy to take some questions.
Thank you, ma'am, for your wonderful speech. So now, if anybody is having their questions, you can just turn on your microphone, or you can just put it on the meeting chat.
I think everything was too clear, or what happened?
Yeah, you can just turn on your microphone, Sri Shuman.
Yeah. Hi, ma'am. Thank you. I'm listening you again. So I have a basic questions like which method is best to protect? Like you mentioned two, three methods.
Yeah.
Yeah. So like which direction we should go further? There are many methods, but which one is more convenient and relevant to do that?
Yeah. So thanks for that good question. It obviously varies. The big question is, like I told you, there's a variation in the kind of composition you could have of the asteroid. Similarly, the size, etc. Right? How much time do we have for preparation? Right? What is the period in which it's going to happen? So I think what we do not actually know the answer to the question. I think it would have to vary depending upon what kind of an asteroid it is, right? What is the composition of the asteroid? For example, that slice and dice method. If you know that your asteroid is made up of porous material, which you can easily break up into pieces, or using some laser ablation, depending on the material, you could actually use lasers. But for example, if you know that that asteroid is basically a metallic one, right? Then probably you would have to think of doing it in a different way. So what I would say is we do not know the answer to that question. It would vary depending upon what what is the asteroid we are talking. So we are still trying out with, that's why we have all these different missions to asteroids, because we are trying to study their compositions, etc. So that would kind of guide us as to what would we have to do, right? Thank you.
Okay. Simultaneously, we have to do like type of asteroid we need to find and then the
Yeah,
protection.
because it could be made up of carbon, silicates, it could be made up of metal, it could be made up of all kinds of things, right? So depending upon the material, the mass, we'd have to, you probably need to this thing. You need to know how much do you need to deflect it, right? So at present, we
Okay.
do not have fixed answers. It depends on the object.
Okay, thank you, ma'am.
Yeah, welcome. Yeah, so I have another question over here, which I can see on the chat by David Clark. How to participate in actual asteroid projects? So the citizen science projects, the ones I mentioned, Astrometrica, the organizers over here, which is a citizen science group run by Sovan Acharya, uh, they actually um, what happens with Astrometrica is you have to actually make teams. So you should register with them. You can contact them, and you can actually you have to register with teams, and you have to define, the team works for a certain period of time, and depending on that, you fix up what you do. The other ones, most of them, you can go onto their websites, right? And from the website itself, they will very well guide you as to what you have to do. And like I mentioned, even Astrometrica, what happens is they even train you, right? If you say, oh, I don't know anything, how do I manage? So that's okay. They actually have training sessions where they train you that, see, the data will come to you like this, and you need to handle the data like this or whatever. So I think you can contact Sovan Acharya sir, or you could actually go onto their websites, and there are quite good descriptions and instructions as to how you should be doing it. So it should not be too difficult. Yeah.
There is one more question in the chat.
Yeah. Okay. 1 minute. Okay. So, what are the conclusions drawn from DART by NASA? Yeah. So, as of now, what we know that the DART mission has been very successful in deflecting, but obviously that system, the Didymos Dimorphos system, was not no threat to Earth. This was just being done as a practice mission. So, in terms of the deflection it did, it is a very good deflection. It would be sufficient if you had to protect the Earth. It would have been sufficient. So it's like that, but obviously we don't know the exact values, and that is why you have the sequel mission, which is Hera, because at present, see, this is an impact. So now the orbit which is there, we do not know whether that is the what you say, that's going to be the constant orbit or it's the fixed orbit, and that is why you're having the Hera mission, which is going to go again over there to later on measure now what is the, after the impact has kind of settled down, then to find out what is the orbit, so that you can actually calculate how much kinetic energy got transferred and what happened, right? So we'll have even better answers after the Hera mission. But the conclusions drawn by NASA was that yes, this is a good thing, right? The kinetic impactor thing is a good option, but again, it all depends upon, like I showed you, right? These asteroids can be in a variety of sizes, shapes, as well as composition. So it worked well for something like that, which was 160 meters in size, right? But again, if you have a bigger one, then it's obviously a different story, right? And the bigger ones is what we are more worried about, right? Which are, let's say, a kilometer size. Yeah, there's another question here from Prakash Singha, which he says, how much time does it really going to take for mining material from asteroids? Okay, so this is slightly science fiction-y about mining from asteroids, but it's just that people know that there are a lot of rare metals. For example, some asteroids in which there's lots of platinum, or there's diamond and stuff like that. So obviously, it's going to take time for people to actually plan, but there's a lot of space entrepreneurship happening of late, right? If you're aware, there are many startup companies in India itself which have started up, which are basically launching satellites. Most of them are these CubeSats, small satellites. But as things get more and more, people get uh, more expertise at doing this, then they would probably consider doing it. So at present, I would say that it would take time, but maybe in the next 20 years, you could be having people actually mining asteroids. It could be possible. Yeah, so I have another question from David Clark. Thank you. Why don't we explode asteroids with nuclear bombs? So actually, that's what happened in Hollywood movies. In Hollywood movies, they actually sent a nuclear bomb, and I think in one of those ones, which one? I think Deep Impact. One of them, they actually sent a bomb and blasted the asteroid. So that is one of the options. I had mentioned that option. But the problem is that this basically means that you're going to put a nuclear bomb onto a rocket, and it should precisely hit that asteroid at the right point. And at the precise time, your rocket has to blast. I mean, the nuclear bomb has to blast. And obviously, this is a reasonably risky thing, right? To be putting a nuclear bomb on a rocket, because you know that even launching rockets also is risky business. And therefore, like I said, it was done in Hollywood, in movies, but in reality, doing it with a nuclear bomb, I think the risk element is pretty large. And then the debris also, because you will not have control about what is happening with the debris after you blast it off. The debris is also going to come, right? And you will not have much control about that. So this thing. I have another question from Sumit. Is it efficient to break asteroids or deflect them in terms of damage done by energy used? Okay, so you see either of the two options is fine. You basically what you have to do is you've got to protect the Earth. You don't want the asteroid to fall on you, right? So one of them is you break the asteroid because you know that if the asteroid has a smaller size, then if it falls on the Earth, it's just going to burn in the upper atmosphere. So it cannot harm the Earth. So you can break it. The other thing is you don't need to break it, you just deflect it. You just change its orbit so it's going to go somewhere else and you're not going to harm the Earth, right? So in principle both of them do the job. Your job is basically to protect the Earth. You do not have to worry about your breaking the asteroid or no. So I think the answer to this question would be it would depend upon which asteroid, what is the what is the uh, uh, you know see, the problem is that if the asteroid is too close, right, then the deflection will have to be very, very large so that you protect yourself. So then in that case, maybe it is better to break it up, right? But if it is far enough, then even a small deflection is enough for it to, change its path and not be a threat to the Earth. So I think that would just depend on individual cases. So at present, we are just trying to build the ground, right? Where we are actually thinking of what are the possible methods, what all can we do, how can we do it. And then probably as we have specific cases, we will actually see what is the one that needs to be done, right? Yeah.
Ma'am, and thank you, ma'am. And is it possible, like, to slow the speed down of the asteroid that is coming so that after we land it, we can mine it and use its resources?
That, yeah, that is also that can be done, but something like that can be done probably, but it'll have to be done with a lot of precision because you want to get the asteroid, but you don't want to break it. You want it to land, right? So in principle, people, yeah, you can do things like that, but it would obviously take a good amount of technical expertise to be doing that. But it could be something that may happen in the future. You may
Thank
do
you, ma'am.
something like that. Hmm. You may do something like that. Yeah. Aritra, yeah,
Yes, ma'am.
I think
I
there's
also,
nothing more in the chat, no?
no, there is nothing on the YouTube chat as well.
Oh,
So I think we can end the session now.
yeah.
So lastly, ma'am, I want to thank you for giving your time and sharing this incredible knowledge with us, and thanking all the participants to join in the session. And for more sessions, you can keep joining these free sessions, or you can attend our master classes on different expertise topics. So thank you all once again.
Thank you so much. Thanks so much.
Thank you, ma'am.
Bye bye.